Hello, my friends. Welcome back. In the previous video, I showed you how you can design a circuit to calculate the third power of a given input, right? And the design, as you can see, was this one in here. I'll probably make a GitHub page or something so that I can put all the codes in there because like these codes are synthesizable, the syntax and everything is fine. And as I said, like I've synthesized them using Vivado. And it's a free tool. You can just download and do it yourself if you wanted to. But yeah, let's get back to this. And we said that this was like an iterative implementation, which means that we cannot begin a new computation until the previous computation has completed, right? And we also mentioned that this iterative scheme is very similar to the software implementation, right? And we also talked about this I valid and O valid signal, which means that we need certain handshaking signals to indicate the beginning and completion of like a computation. And the external module that sends the data in also needs to use the same handshaking. All that being said, this is a fine design. It works. And we calculated the throughput. We said the throughput is, because we're calculating in this example, data width was 8 bits. So we're calculating 8 bits, right? We're processing 8 bits in 3 clock cycles. Each calculation needs 3 clocks. And then we have to wait for the first calculation to finish so that we can start the second one. So the throughput was 8, which is this number here, divided by 3. So it's like about 2.7 bits per clock. And then we did mention that the latency of this clock, this design is 3 clock cycles, right? Which means that once an input is valid, it takes 3 clocks for the output of that specific data to be valid. And also the timing is the delay of a 1 multiplier in the critical path. So far, everything is so good. In today's video, I want to show you how we can take this design and make it a bit more optimized for throughput, right? We can optimize this design for area, for power, and for speed. And when it comes to speed, is like optimization for throughput, for latency, for timing, you know, a lot of different optimization that depending on what you need, you can, you know, take advantage of those techniques. But in today's video specifically, I want to talk about how we can improve the throughput, right? Because right now it's 8 bits divided by 3, which is very low. Okay, how can we do that? Basically, all we need to do here is to pipeline our design. This is the best known technique to improve the throughput of a design. And by pipelining means that we want to be able to store the value, because like data comes in, right? But the reason that I cannot do anything until this calculation is done because as soon as I change data, everything is going to be messed up. I lose the old values and I cannot do anything with that, right? So if there was a way that I could save the previous values as the new data comes in, then I could calculate more. I could process more data back to back. This is the concept of pipelining, right? So the data keeps coming in, like you get a new data every clock cycle, right? And then you save it and you deal with the saved values. And then like after 3 clocks, you can just update the saved values. Okay, let's see how we can do that. I'm basically gonna copy this file in here because it will be very similar. And I'm just gonna go here and go throughput, optimization, and then I can paste my design here. We don't really need the I valid and O valid, so I'm just going to keep it out. You can still have that. You can say, okay, at the positive edge of the clock, if the data was valid, then do this calculation. But the thing is, like once you're dealing with pipeline design, the whole point of pipeline is that the data is coming in continuously and you're not supposed to have gaps in your data, because if you have gaps, the performance is just not as good, right? And there is no point of pipeline its design. But again, you can have that, no problem. But for the sake of this video, I just want to take them out so that we can show you how we can, deal with the main functionality of the pipelining. Anyway, I do not need these. I don't need this. Obviously, I can just delete that part, and then I can copy this, and I'm gonna put that in here, and copy that, paste that. Let's do this, and I want to go x1 and x2. So x1 and x2 are registers that I'm using, right, to save the values of iData. So a new iData comes in, and x1 and x2 are basically delayed versions of our data, right? So let's say the iData in the first clock is 5, in the next clock x1 is 5, and in the second clock after that x2 is 5, right? This is how it works. So x1 is a delayed version of iData, and x2 is the delayed version of x1, which is the second delayed version of iData. And same thing goes here for xp1 and xp2. And you can tell by the data width that this is supposed to be like holding the values of intermediate calculation that we're doing. They don't necessarily need to be this big, but again, I don't really want to optimize it in terms of like how big of a register I'm using. So we don't have this anymore. I'm just going to get rid of that, and then I can get rid of that as well. And then I'll go here, and it's a super simple design. So all I want to do here is to go in stage 1. It's a pipeline design. It has like different stages. In the first stage, I want to go x1 is iData. So it gets the value of the iData, and the next clock the value is assigned. And then I can go xp1, right? That's also iData, right? Note that xp1 and iData, they don't have the same data width. So this is, 3 times data width. So like if the data width is 8-bit, this is like a 24-bit value, and this is like an 8-bit value, and we're assigning an 8-bit value to a 24-bit value. A better practice would be just to zero pad the rest of it. But again, Vivado is smart enough to understand what you're doing here, and it only assigns this to the lower 8 bits of xp1 and keeps the second bits unchanged. And obviously you can like modify this design as well. Like you can just go have that. Oh, I have like a reset, and at reset you set x1, xp1, x2, and xp2 to 0, or even maybe all data, and like have a proper design. But again, that is not the scope of this video. I just want to show you that the core functionality of optimization, how we can optimize our design. Then you can play with that, and if you had any questions, you can obviously let me know in the comments, and I'll be more than happy to answer your questions. Anyway, that was all we needed to do in the first stage. And in the second stage, I'm just going to go stage 2. What's happening here is that I want to go x2 now gets the value of x1, which I said like it's a delayed version of x1, and then xp2 now is xp1, right, times x1, right? So it's basically the second, like its iData squared is stored here. And finally, the third stage, which is the last stage, we can just go OData, right? Oops. We can go OData is, and then my OCD kicks in here. Need to align these by the way. And then here I go xp2, right? And I just need to multiply that by x2. And that's it. This is the core functionality of a pipeline design. And here is like another way of calculating the third power of a given input, but a pipeline design. If you calculate the performance, if we want to talk about the performance of this design, we can say that the throughput is 8 bits, right, per clock, because the first input comes in and it takes 3 clock cycles for that to output something. And then the second data, and then the third and fourth, and then so on. But once your pipeline is full, like after the third data, right, you're outputting something, which is the correct calculation of the previous inputs, right? So you're outputting valid values every clock cycle. So which means that you're processing 8 bits per clock as you're processing 8 bit in each clock cycle. So your throughput is now 8 bit per clock cycle, which is 3 times faster than the previous implementation, right? Your latency is still at 3 clocks because it takes 3 clocks for the design to output the thing, the output of the, the third power calculated values of the input. And the timing hasn't changed. It's still the delay of a 1 multiplier in the critical path. That's how your timing is defined here, right? And the other thing that I wanted to say is that the throughput performance obviously has increased by a factor of 3 over the iterative implementation. And in general, when an algorithm requires n iterative loops, and when you unroll that, then the pipeline implementation probably has can improve the performance in terms of the throughput by a factor of n. Okay, that's something to note. And then the other thing that I wanted to mention is that in this example, as you saw, there is no penalty in terms of latency, right? Your latency didn't change with the pipeline implementation, but the throughput will come at the cost of area. We will talk about area later in the next videos. But you can tell, like I'm using 4 different registers, right? And these registers, like these 2, each are like 8 bits, and these 2 each are like 24-bit values. So I'm using resources on FPGA to store the data, right? So everything is a trade-off. I'm improving the throughput, then what am I giving up? In this example, it was the area. But yeah, like every design has a different specification, right? Sometimes they want you to have a design which is like super fast in terms of throughput, and they don't care as much about the area. So like this is a technique that you can obviously use. In the next video, we will talk about how we can optimize the same design for latency, and then for timing, and then speed optimization would be done, and then we can move to power and area. I hope you enjoyed this video. If you did, please like it. It helps me a great deal. And if you haven't already, please do not forget to subscribe to my channel. And thanks for watching this. And I will see you all in the next video. Take care. Have a good one. Bye-bye.